So this is some data that we took from our lab, which we published in 2013. And what we did in this study, this is to kind of just demonstrate some of the variables at this point, is this was a study where we looked at the impact of blood donation on key hematological and also cardiorespiratory variables. But here we've got in the unbled state, this is a standard concentration that you would see. It's around about 155 grams per litre, which is the equivalent of about 15.5 grams per deciliter, which is a standard score that you would see for the population. It does vary on training status. The concentration is dependent upon age. So as we get older, the hemoglobin concentration starts to decline with age. We see differences between males and females. Males have generally a higher hemoglobin concentration than females, predominantly because of a larger surface area in males compared to females, and that's kind of a generalization. Here's the hematocrit. So this is our hematocrit concentration. So remember that we referred to previously the hematocrit to erythrocytes. So this is the hematocrit as a percentage. So we've got a 48.76% hematocrit. So roughly about a 51.25 concentration for hemoglobin, for erythrocytes in comparison. This is then the erythrocyte count. So this is just kind of not a percentage. So these are the three we're going to deal with. Don't worry about these values here, which are in essence to do with blood lactate concentrations. But what you can see here is what happens when we donate blood. So the kind of thing that most people do is they will donate blood as a kind of a process that we generally do. And you can see the effect. You donate in the region of about 450 millimeters, so around about just under half a litre of blood when you make a standard donation. And what you see here is this is the effect. This is the effect which is taken 24 hours post donation. So the participant has donated. This is what's happened to the hemoglobin. So the hemoglobin has fallen, a significant reduction, quite significant, from a 155 to a 141. The net result is that we've got a decrease in plasma, in hematocrit concentration as well. And that's quite interesting, because you might go, well, hold on, that doesn't quite add up. Why is it that the hematocrit concentration has fallen? Why hasn't the hematocrit concentration expanded to compensate for the drop in the erythrocyte count? Well, of course, what you've got to remember is that some of the responses are more instantaneous, some of the responses are perhaps slightly slower. So one of the things that we know is the change in an erythrocyte concentration, for example, has a very fast reaction when we expose somebody to conditions like altitude. The plasma volume does not expand at such a fast rate. It actually has a slightly delayed response to it. So what you would actually start to see is, because we've drawn volume off, so we've fundamentally reduced the blood volume by about half a litre, the net result is there is a proportional decrease in the amount of aqueous fluid, the plasma. So because we've just got a massive reduction in blood volume, the plasma volume has decreased as well. That plasma volume, represented here by the hematocrit, will bounce back despite the reduction in blood volume over time. And so here you can see the net effect of this blood donation. So here we've got the blood donation pre to post, and you can see why understanding about hematology is really important. Look at the consequent effect on the VO2 max values. So the VO2 max value is our proxy indicator of cardiorespiratory fitness. It reflects that, as we referred to, that interplay between the cardiovascular, the respiratory and the muscular systems. And you can see here it's got a reduction from about 51.3 mils per kilogram per minute to about 48.4, and that's over a 24-hour period. And you can see that both in the relative and the absolute scores for this. The net result of this is it's affected what is called the gas exchange threshold. So in terms of the time taken to reach the gas exchange threshold. And the net result of that, what does that mean? Well, fundamentally, the gas exchange threshold represents the transition from predominantly aerobic to anaerobic metabolism. Now, if you want to know more about that, there is a session provided which is on what the gas exchange threshold is another session, and what it and how we detect it. But fundamentally, treat it as what it is, which is that direct representation of the transition from predominantly aerobic to anaerobic metabolism. It had an effect then on the GET to N test. So fundamentally what's happening is despite the fact they then got to this point earlier, what is fascinating is then their time taken to the end of the test actually got longer. Well, actually, there's a logical reason to that. Once we shift beyond the gas exchange threshold, which is our indicator for the transition from aerobic to anaerobic metabolism, we're relying more on the anaerobic energy. But by donating blood, and therefore reducing the oxygen carrying capacity, we are not actually affecting the anaerobic capacity. We're affecting aerobic energy release, not anaerobic energy release. So the net result is, although they got to gas exchange sooner, that transition, they barely really tapped into the anaerobic energy release, and so we've not directly affected. So the net result is they're spending longer getting to the gas exchange threshold. But all of those kind of summarised fundamentally demonstrate that the blood volume, the erythrocyte concentration, the plasma volume have significant impacts on the outcomes in terms of things like VO2 max, which is our measure of cardiorespiratory fitness, and our kind of aerobic capacity-based measures. And you can see this data here. So this is data taken from a PhD student who was at ARU in Cambridge. And what in this study they did was they asked participants to donate blood. And then they reported back to the laboratory on successive days. And so you've got here, blood donation takes place at this point here. So this is day 1. And then they donate, so day 2, so that's 24 hours, 48 hours, 72 hours, and then 96 hours post-donation. And what is really interesting is this is the donating group, is that what you can see is, yes, you get the rapid reduction in hemoglobin concentration because we reduced blood volume by 450 mils. So we've got less blood, total blood, therefore we've got less oxygen carrying capacity. But notice that even though we've donated the blood and we've donated it here, at 48 hours, the hemoglobin concentration keeps falling. It's still falling at 72 hours, and by 96 hours, we have not got anywhere near to bouncing back. So this is actually, really demonstrating the kind of the kinetics that we see when we donate blood, and the kinetics that we see in terms of the bounce back. In the unbled state, this is our population group who didn't donate blood. Yes, it's gone down, but these are considered to be, there's no real significant change here. This just reflects kind of variability in the group over the course of the week. And this here fundamentally represents our kind of average, our kind of baseline measurement. But it is quite fascinating to see this, that if you reduce blood volume, because you've taken whole blood volume down, and a reduced plasma volume, you're going to have reduced erythrocyte count, and the erythrocytes are on which the hemoglobin concentration sits. But it's the fact that it keeps declining up to 72 hours post-donation that is of real importance, and has ramifications, of course, on why we may need to think about what we do in terms of exercising post-blood donation, for example.